Primary and secondary amines are considered weak acids. If we use a strong enough base, we can remove the nitrogen to hydrogen proton. For example, an alkyl lithium like butyllithium can remove the hydrogen on diisopropylamine to form a base that is very useful in organic chemistry called LDA. LDA is short for lithium diisopropylamide. This is a base that we talked previously. We typically use them to make enolates out of ketones, aldehydes, and other carbonyl compounds. Amines are better known as a basic functional group, and so they react with several acids. Their basicity is typically measured by the pKa of the conjugate acid that forms from a reaction with an acid. The larger the pKa of the conjugate acid, that means the weaker the conjugate acid is, and the stronger the amine base will be. Here's a general example of an amine reacting with an acid, forming an ammonium salt, which would be the conjugate acid. Measuring the pKa of this conjugate acid will indirectly give us a sense of how strong of a base we have with the amine. On this slide, we have a list of several amines and a list of the pKa values of their conjugate acids to measure indirectly how acidic these compounds are. Ammonia, when it reacts with an acid, becomes an ammonium salt. In other words, it will have 4 hydrogens and a positive charge on the nitrogen. This is the conjugate acid that forms when it reacts with a Bronsted acid. The pKa of that conjugate acid is 9.26. You might recall that we mentioned that the higher the value, the stronger the base is. So the pKa value really refers to how acidic the conjugate acid is, and the higher it is, the less acidic the conjugate acid is, which means the stronger the base. Comparing ammonia to the next example, which is ethylamine, notice the pKa value goes up for the conjugate acid, which means this is a stronger base than ammonia. One way we could rationalize this is that the ethyl group is an electron donating group, and so we can think of that nitrogen as being more electron rich, and it can react with an acid easier. Another way to think about it is the stability of the conjugate acid. So when ethylamine reacts with an acid, it will form the following conjugate acid. So NH3 plus an ethyl group will also have a positive charge on the nitrogen. This ethyl group is an electron donating group, so it helps to stabilize the positive charge on the nitrogen. It makes this reaction more likely compared to the reaction with ammonia. The next example follows the same trend. So we have diethylamine, 2 ethyl groups, which are both electron donating. So the pK value of the conjugate acid is slightly higher, which means the base is slightly stronger than ethylamine and also ammonia. The next example is a typical amide. This nitrogen on the amide is tied up in resonance with the carbonyl. So the lone pair on the nitrogen moves or can be used to move electron density into the oxygen, creating this other resonance structure. As a result, that nitrogen, although at least the lone pair on it, is not readily available to react with an acid or even electrophiles. So for that reason, it's a relatively poor base, as shown by the pK value of the conjugate acid. The next 2 examples show pyridine and pyrrole, which we talked about previously. Note that the lone pair on pyrrole, this compound here is required for the aromaticity of pyrrole, and so it's not as readily available as the lone pair on pyridine, which is not necessary for aromaticity of pyridine. And so that's illustrated by the pKa values of their conjugate acids. So pyridine is a stronger base since the lone pair on the nitrogen is not required for aromaticity. Aniline, compared to other alkyl amines at the beginning of this table, is a fairly weak acid. The reason is the lone pair on the nitrogen is tied up in resonance with the aromatic ring, as shown by this resonance structure. As with many acidic and basic functional groups, substituents on a compound will affect the acidity or basicity of that functional group. Anilines, like many amines, are basic, and substituted anilines will be affected by any substituent that is placed around the aromatic ring. For example, if we add an amino group, the pKa will go up slightly for the conjugate acid compared to not having that substituent. The same thing occurs with a methoxy group or a methyl group. These are groups that are considered electron donating. And so if you imagine having one of those groups here, we can push electron density into the ring, which means also that this nitrogen is more electron rich. It is going to be a better base compared to not having those substituents on the ring. The halogens, a nitrile and a nitro group, are all groups that are electron withdrawing, and so they will make the nitrogen less electron rich, and so it will be less of a base compared to not when those substituents are not in the ring. In this question, we're going to do a comparison between the basicity of dimethylamine and pyridine. The pKa values of their conjugate acids are given in the question. For dimethylamine is 10.73, and for pyridine is 5.25. Pyridine, you might recall, is an aromatic compound that is a 6-member ring involving 3 double bonds, 1 nitrogen atom, and 5 carbons. In this question, the pKa values of the conjugate acids of the two amines we're comparing are given. For dimethylamine, the pKa of the conjugate acid is 10.73, while the pKa value of the conjugate acid of pyridine is 5.25. Based on these values, we can determine that the conjugate acid of dimethylamine is a weaker acid, which means the base, dimethylamine, is a stronger base than pyridine. In this question, we want to rank the following compounds in ascending basicity. We have 3 molecules: para-nitroaniline, para-aminobenzaldehyde, and para-bromoaniline. In this question, we want to rank 3 different substituted aniline compounds in terms of their basicity. In questions like these, we often get a mix of electron donating groups and electron withdrawing groups, but in this particular question, all 3 examples involve an electron withdrawing group. In order to figure out this question, we want to think back at electrophilic aromatic substitution, and you might recall that we had halogens rated as a weak deactivating group. In other words, is a electron withdrawing group that is only a weak electron withdrawing group. Aldehydes, like most typical carbonyls, were considered moderate deactivating groups. In other words, they're stronger electron withdrawing groups than halogens. And we also talked about nitro groups, which are strongly deactivating in terms of the electrophilic aromatic substitution, which means they're very strong electron withdrawing groups. So that sort of gives us a hint in how to answer this question. Generally, electron withdrawing groups will make an amine, including anilines, less basic. So for example, this para-substituted nitro compound will have a very strong electron withdrawing group that makes this nitrogen a very poor base, since it is very electron poor. The next example, with the aldehyde, we have a moderate electron withdrawing group. It makes the nitrogen electron poor, but not as much as the example with the nitro group. And then the bromine, again, is an electron withdrawing group, but it's a weak electron withdrawing group. And so this should be the most basic out of the three. If we had an example with an electron donating group, that should be a stronger base than any of these three molecules.